Hello everyone. In this video, we will be solving a numerical problem based on the boundary value solution to Laplace equation. Now, in this question, it is given the two concentric shells, one r equal to 20 centimeter, another at r equal to 30 centimeter, are held at potentials. First one is at potential 0 volt, the second one is at 50 volts. If the space between them is filled with the dielectric material with epsilon is 3.1 epsilon naught and sigma is 10 power 12 Siemens per meter, we are asked to find voltage, electric field intensity and electric flux density in the region between the two, and also we have to find charge densities on the shells. So let us do the problem. First, we will write down the boundary conditions. In this case, the first boundary condition says at r equals to 20 centimeter, which is 20 into 10 power minus 2, voltage is 0 volts. And the second boundary condition says at r 30 centimeter, 30 into 10 power minus 2, voltage is 50 volts respectively. These two are the boundary conditions. Also, epsilon is 3.1 epsilon naught. Means here in this case, epsilon r value is 3.1. Also, conductivity is given 10 power 12 Siemens per meter. Now, we should use Laplace equation. Since these are concentric spherical shells, we have to use del square V in spherical system of coordinates. So let us use the formula for del square V in spherical system. This is the formula for del square V in spherical system. Here in the question, it is given between the two concentric spherical shells, the potential has to be found. For this case, potential will be a function of 1d r. In that case, differentiation with respect to theta and phi will be made 0. Only the first term will be left. So I'll be writing that 1 by r square d by dr of r square dv by dr equals to 0. Now this r square, if I bring it to the right hand side, multiplying with 0 will give 0. Thereby, I will get d by dr, r square dv by dr equals to 0. Now, we should perform integration with respect to r. I'll be writing integrating with respect to r. Removes the first differentiation here, which will give r square dv by dr equals to integration of 0 is 0 plus integration constant c1. Now, we can rearrange these terms. This r square can be brought to the right hand side. dv by dr is c1 by r square. Now, one more time integrating with respect to r will give the potential function v. So integrating with respect to r, v equals to integration c1 by r square dr. So that is going to give c1 integration of 1 by r square is minus 1 by r plus integration constant c2. So voltage is minus c1 by r plus c2. Now, by applying the boundary conditions, we have to find what is C1 and C2. Let us take the boundary conditions from here. So I'll be copying the boundary conditions from here. And by making use of these boundary conditions, we will find what is V, which is a function of R. So let us make use of these boundary conditions and solve. So first, applying this first boundary condition will give, first boundary condition application will give 0 equals to minus C1 by 20 into 10 power minus 2 plus C2. And applying the second boundary condition will give 50 equals to minus C1 by 30 into 10 power minus 2 plus C2. Now we have to solve for these two equations. These two equations can be solved, which is two equations with two unknowns. By solving this, we will be getting the values of C1 and C2. I'm leaving this solution for your exercise. I will give the answer. So the answer for C1 is 30 and the answer for C2 is 150. Thereby, the potential V function can be written as minus 30 by R plus 150. This is potential, which is a function of R in volts. So I will be writing for better understanding V, which is a function of R in volts. Now we should be doing the estimate of electric field intensity also. So finding electric field intensity is minus del V. So minus del V formula is minus minus dou V by dou R A R cap plus 1 by R dou V by dou theta A theta cap plus 1 by R sine theta dou V by dou phi A phi cap. This is E, and you will be getting differentiation of this with respect to R alone, because B does not have any theta variable or phi variable. Those two differentiations will be 0. So now your electric field intensity vector is going to be minus differentiation of this with respect to R. That is minus 30. 1 by R differentiation is going to be minus 1 by R square and plus 150. So differentiation of 150 is 0. AR cap. Thereby, electric field intensity vector E can be given as minus 30 by R square AR cap, and this has to be written with the units volt per meter. Now we should find what is the flux density vector D. So flux density vector D formula is epsilon times E. We have been given with epsilon value, which is 3.1 epsilon naught into E vector, which is minus 30 by R square AR cap. So epsilon naught value we can write. I will be giving the epsilon naught value. Epsilon naught value is 8.854 into 10 power minus 12 farad per meter. Or you can write epsilon naught as 10 power minus 9 by 36 pi farad per meter. So this is from the equation 1 by 4 pi epsilon naught is 9 into 10 power 9. From this, you can write epsilon naught as 10 power minus 9 by 36 pi. So either you can use this value or you can use this value to find. So I'll be using this value for the easier representation. So we can write D as 3.1 into 10 power minus 9 by 36 pi multiplied with minus 30 by R square AR cap. So this 10 power minus 9 can be written as nano. So when we simplify this, we will get minus 0.8227 by R square into 10 power minus 9. This 10 power minus 9 can be written as nano. So we know 10 power minus 9 can be written as nano, which is indicated as small letter n. So nano coulomb per meter square is the unit for flux density, and the direction is AR cap. This is the vector D, which we have found. Now, the next subdivision is we are asked to find the charge densities on the spherical shells. So let us proceed to find the charge densities on the spherical shells. So we have to find charge densities on the shells. From the flux density vector, we can find charge density. We know these are the concentric spherical shells. So one shell is at a radius of 20 centimeter, another shell is at a radius of 30 centimeter. So 20 centimeter and 30 centimeter are the corresponding radii of the two concentric spherical shells. The charge densities will be in the form of surface charge density, because on the spherical surface, the surface charge densities are going to be present. Surface charge densities for rho S1 and rho S2 we have to find. That is the second subdivision. So let us try to find the charge and flux density relation. We know as per the Gauss law, charge can be found as closed surface integration D dot ds. And we can also write the surface charge densities in terms of charge, or we can write charge Q as surface integration rho S ds. Now, when we look at this equation, so when we equate these two, we can get the magnitude of vector D is equal to rho S. So we can find the rho S value from the flux density vector. So we can take the magnitude of this at the particular value of the radii to get the charge densities on that particular shell. So if we consider here for the inner shell at R equals to 20 centimeter, this is for the inner shell, inner spherical shell. For this, we can find the charge density rho S as magnitude of D at the value of R is 20 centimeter. So which can be minus 0.8227 divided by r square nano. So we can write this as nanocoulomb per meter square. We know surface charge density also carries the unit coulomb per meter square. Charge per unit surface area. So nanocoulomb per meter square. We can substitute R value as 20 centimeter. Thereby we will get what is the surface charge density at that particular shell, inner shell 1. So rho S1 will be equal to, I will be writing the answer directly for you to refer. So for 20 centimeter, the answer is going to be minus 20.56 nanocoulomb per meter square. So this becomes the magnitude. Let us understand what will be the sign later. So let us consider only the magnitude here for now. And rho S2. Now at R equals to 30 centimeter. This is the outer spherical shell. For the outer spherical shell, we can estimate similarly rho S2 as magnitude of D at R equals to 30 centimeter, which is going to be magnitude of minus 0.8227 by R square nanocoulomb per meter square. Now, by substituting R as 30 centimeter, rho S2 is going to be 9.137 nanocoulomb per meter square. So this is just the magnitude. Now let us try to understand which has the positive charge and which has the negative charge. So we have to understand the inner shell is at R 20 centimeter and the outer shell is at R 30 centimeter. And by looking at the potential difference or potential values, we can understand what is the direction of the electric field intensity or flux density. Inner one is at 0 potential and outer one is at 50 volts. Now, when you look at the electric field direction, electric field is always in the direction of decreasing potential. Means from higher potential to lower potential is the direction of electric field intensity. If I consider from higher potential to lower potential, and the charges occupying here will be outer one is at positive charge and inner one is at negative charge. Always electric field is directed from positive to negative. So the outer one will be having the magnitude which is positive charge and the inner one will be at a negative charge storage. That indicates the potential difference. Wherever the higher value of potential is there, there is the positive charge, and wherever is the lower value of potential is there, there is the negative charge. Accordingly, I am giving the signs for the charge densities. Charge density talks about charge per unit area. Here we can relate rho S and D magnitudes are going to be equal from these two equations. And thereby magnitude of D we are finding, and the signs are assigned depending on the voltage from one shell to the other shell. So this is how we have to solve for charge densities on the spherical shells. I hope you have understood this problem. Thanks for watching the video.